Hi, let's talk about wind. We all know what wind is, right? You know when the sun hits the earth and its heat distributes but not evenly, causing the movement of air currents. Places like the coast, desert, get more wind because of the specific heat capacity where the heating is more uneven. That's only the gist of it. How do you use it? Hey class, it's only the start. Don't fall asleep on me now. Earlier I said that energy starts from the sun, then turns into wind, then spins a turbine, and we have light. From earlier times, simpler times might I say, people were utilizing the power of the wind. For example, farmers and small houses could rely on windmills to power their lifestyle, extracting roughly 3 kilowatts per day. Nowadays, windmills can stand 30 times larger and produce into the megawatts. They are long and constructed to capture the most wind, but due to stress of strong wind being so high, the blades wear and require a lot of maintenance, which is often pricey. Also, the only effective wind speeds that can be extracted are 6 to 14 meters per second, and only 1/4 of that energy can be converted into electrical.
This is our great big plastic wind box of science. These lights represent the sun. This ice represents the north and south poles. So here's what happens. Energy from the sun heats the land, and the land warms the air over the land. The air molecules get going faster, and they spread farther apart, so they don't weigh as much for the room they take up. So cold air can push the warm air up. That's why we say warm air rises. So look what's happening. The smoke shows us that the air is sinking over the cold poles, flowing over the cities, and then rising over the warm parts. See, it goes around in a great big circle. And that's what happens on the Earth. Now there's one more thing. The Earth is spinning, so the wind starts spinning. That's why wind comes from all different directions. Wind is wild.
Bill Nye the Science Guy.
What do you think that is?
A tail. It's
Some sort of cosmic device? No. This
a dream catcher.
This is what this will do. As the wind spins around, it'll give you your wind direction. So it looks kind of weird, but serves a very neat little purpose.
It also lets you steer the ship.
No, it gives you wind direction.
Oh. And the conning tower is for?
Wind speed. So if you're full of hot air,
And
like
the hot,
I am,
and the
you
hot
can
tub?
test it. That gives you rain.
My uses for these things sound a lot more fun than yours.
Well, mine sound a lot more useful.
Welcome to Sri Science Tech Tweets. What anemometer measures?
Anemometer is the device used to measure the velocity of wind. The word anemometer is derived from the Greek word anemos, which meant wind. This device records the velocity of wind in terms of meters per second or NATS, nautical miles per second. An anemometer is designed based on the principle of rotator motion of an embedded fan. As the velocity of the wind increases, the blades of the fan rotate with more speed. Velocity of the wind can also be measured by calculating the pressure formed by the air in a thin glass tube. As the velocity of the air entering into the tube increases, the pressure applying on the already existing air or liquid inside the tube also increases.
What you have seen so far is really the theory and operation of a basic AC generator. But our purpose was to explain the principles of operation of a DC generator. To get direct current, we will attach each end of the conductor to a segment of copper, forming a commutator. Now our machine is a DC generator. The commutator rotates with the loop. Stationary contacts, carbon brushes, ride on the commutator segments. They provide a means of connecting a meter or any other load to the generator. The loop of a conductor, wound on a rotor, and the commutator are referred to as the armature. As the loop revolves and the EMF in the conductor reverses polarity, the connections to the load are also reversed, and the current flow will maintain the same direction externally.
primary objective of designer in wind turbine design is to maximize the aerodynamic efficiency, or power extracted from wind. But this objective should be met by well-satisfying mechanical strength criteria and economical aspects. In this video we will see impact of number of blades, blade shape, blade length, and tower height on wind turbine design. As number of blades on wind turbine increases, aerodynamic efficiency increases, but in a diminishing manner. When we move from 2 blades to 3 blades design, there is an increase in efficiency of 3%. But when we move from 3 blades to 4 blades design, efficiency gain is marginal. As we increase number of blades, cost of the system increases drastically. Along with that, mechanical design
What we did was add a windmill with rotating flaps and a heavy flywheel. When a breeze hits the windmill, it turns the flywheel that's connected to the electrical generator. With the greater surface area and the added inertia of the heavy flywheel, you'll be able to connect it to a larger generator and produce more electricity. A 3-blade wind turbine and the root wind turbine both rotate in the same diameter. But here's the difference in surface area: the 3-blade model and the root wind turbine. It's like a sailboat. If you want it to move faster, you just put up all the sails to collect more of the wind's energy.
The best rotor to do this, in theory, would have a single aerodynamic lifting blade. By contrast, a wind turbine rotor with 10 blades or more is generally considered a bad design to generate electricity with. A rotor with, say, 20 blades would be too heavy, have too much aerodynamic drag, and it would turn too slowly to generate much electricity. A single-bladed rotor can capture more wind energy and generate more electricity than a 10-bladed or a 20-bladed rotor can. In reality, modern wind turbines have 2 lifting blades for better balance, which reduces the wear and tear on each blade. How then does one explain the success of the American farm windmill, which had anywhere from 10 to 20 drag blades?
Now, if I rotate the one on the left anti-clockwise once, it's got 8 teeth. Each tooth engages with the tooth on this wheel, and this means that although this rotates only once, so I'll say it rotates once, this one will rotate actually twice. Now normally when we're defining ratios, we put it down as, say, we can say the ratio here is 8 to 4. But of course we can simplify that, and in fact the ratio is 2 to 1. We would say that if this is the drive, we'll call this one the drive, and this is the driven gear, then what we've got is a gearing up of 2 to 1. However, if this was the drive gear, if this was the one I was turning, I will find that this one will turn slower, and then I would say a gearing down of 2 to 1. So don't get confused. We either gear up or we gear down. Whatever happens, it's the number of teeth on the wheel that tells me how fast one wheel will go compared to the other. It's very simple. Keep it simple.
Start off, talk about average power for a little while. Power, like I just said, energy divided by time. I'm just repeating that because it took me a long time to learn that. I'm just finally getting it, which is pretty pathetic. So power is measured in watts. Energy is measured in watt seconds, or joules. So if somebody came up to you and said 20 kilowatts, you would know they were talking about power. If somebody said 20 kilowatt hours, you would know they were talking about energy.